So in this video, I want to go over the results and interpretation of the batting data, and also talk a bit about this thing called exchangeability. So the first thing we want to do anytime we've got data of any kind, irrespective of the analysis that we're going to do, is just look at the data. And so what I've got here is the number of times people batted, and this is just a histogram. And you can see that it appears to be a skewed distribution. But if we look at it with a little bit more detail and granularity, we can see that there's a big difference among the different positions. So for most of these positions, you can see a fairly uniform distribution of times batted over a range about 0 to 600. But pitchers are clearly anomalous because they rarely bat because a pitcher doesn't play in every game. So this skewed distribution is really a combination of a uniform distribution for 8 of the 9 positions combined with that distribution for the pitchers. Another thing we're going to obviously be interested in is average, which is the batting average, which is determined by taking number of hits and dividing by at-bats. Again, we've got a histogram. Now, if we think about what this batting average means, well, think about our likelihood function. The number of hits was assumed to arise from a binomial distribution with parameter n, which was at-bats, and theta we can think of as batting ability. And clearly, there's going to be a relationship between batting ability and the batting average. And in our discussion, perhaps we might want to think about what exactly does this theta mean. But in any event, if we look at our histogram, we see something that appears to be bimodal. But again, I think that's driven largely by the pitchers. So if you think of all these other positions, they seem to average out around 220, 230, something like that. In contrast, when we look at the pitchers, they tend to have a very low batting average because the reason a person is hired to be a pitcher is because their ability to throw the ball, not because of their ability to hit the ball. And that's going to have implications later on. So if you think about the way we wrote our code, one of the things we have to specify is the variables that we want to monitor. And here's the variables we chose to monitor. And what's conspicuous by its absence is theta. So what do we think of theta? There's our theta. Theta is the batting ability, kind of related to the batting average for each of the 948 different players. And the reason I didn't put theta in here is that if I printed the output, I would wind up with 948 values of theta associated with the 948 players, and that would just be ugly. So that's why theta is missing. So now let's look at some of these results. So if we look at some of these results, we can see that the pitchers are really different. So, and I should note that this particular table here is not the actual JAGS output. I took the JAGS output and I made this table from it. So this variable here, position, with all these names, isn't going to show up in the JAGS output. I just put that in there to keep us oriented. And I haven't included all of the variables that are available to the JAG output, just those that I thought were most important. But in any event, one of the things we're likely to be interested in is what is the batting ability associated with these different positions, and those are going to be the 9 different values of omega. And it's clear that pitchers are different. So we think pitchers, their median is 0.123, whereas for all these others is much higher. Again, a reflection of the fact that pitchers are hired for their ability to throw the ball, not to hit it. In fact, if you look at the credible intervals, the upper value of the credible interval for pitchers is lower than the lower credible value for all the other positions. And again, it's always a good idea to look at the posterior plots. So these are the posterior distributions. For omega for pitchers, and omega, let's say for 9, is the right fielder. And you can see that if you look at the mode or near the mode, pitchers don't hit very often, whereas right fielders often do. And you can also see some anomalous results here. If we look at these, the effective sample size, it's much lower for pitcher than it is for these other folks. So, the pitchers are clearly different. And the idea of the pitchers being very different leads me to consider, having gone over some of those results, this idea of exchangeability, which I confess I don't have a really deep understanding of. But what I'm going to do is give you the way that I tend to think about this. So let's think about these different omegas associated with these different positions. So the prior for those omegas was a beta distribution which had its own mode, omega 0, and its kappa 0. And if we come up here, we can look at omega 0 and our best guess, if we take the median as the best guess, of omega 0 was 0.228. If we look at kappa 0, if we use the median as our best guess was 56, what I've drawn here is a beta distribution with omega 0 of 0.228 and kappa 0 of 56. And the whole idea is that omega 1, omega 2, omega 3, they're all drawn from this beta distribution with this value omega 0, which is the overall ability of baseball players in general to hit the ball. But here's the thing we need to think about. Is it realistic to think that all 9 omegas, one per position, are drawn from the same beta distribution? Yeah, I don't know. Pitchers look different to me. Is it reasonable to think that what we've got is this beta distribution, and just by chance, the pitchers happened to come at this low position? Well, I'm not sure. I don't think the reason we got this really low value for the omega for pitchers was because it was just an unlucky draw. I think it happens because pitchers, as I said, don't get paid to hit the ball. They get paid to throw the darn thing. And so That's what this whole idea of exchangeability is about, is that, when we think about these omega 1s, omega 2s, all the way up to omega 9, are these just like random labels and we could exchange one for another? Or is it more likely that there actually is meaning attached to these numbers? That a 9 is inherently different from a 2 or a 7 because this is a picture and the others aren't. The other reason that this becomes important, I think, is this whole idea of shrinkage. Because if this is our assumption, that all 9 omegas are drawn from some beta, then what's going to happen is presumably the value of picture will affect our estimate of omega 0, and that will in turn affect the omegas for the other positions. And we saw that in spades when we had Tony and Reginald. So remember, Reginald got 3 out of 15 correct, and Tony got 4 out of 5 correct. Most of the data sat with Reginald. So when it came to estimate the value of omega, remember, omega was the overall skill of the teacher to coach the student. Our omega value was quite low. And as a consequence, Tony, who scored 80% in an exam, might have received a value on his transcript as low as, I just made those numbers up, but maybe 40, 42, maybe 45%. And so I think the main message here is that when we're doing this Bayesian data analysis, we got to really think clearly about what's happening under the hood and the implicit assumptions that we're making and whether or not we really like those implicit assumptions.